Hey, Mr. Martin with the video over partial fraction decomposition. Okay, so Mr. Martin has been using some canned notes that he's been retyping. A typo that can be found on number 2 is the values are correct. They are in the wrong order. A should equal 3, B should equal -1, and C should equal +1. Okay, so partial fraction decomposition is not a method for integration. It is a method to set up a problem for integration. So partial fraction decomposition has 3 forms that we will consider. Everything else is way too complicated to do by hand. So the first is you have a denominator that can just be factored like you would in algebra, where you take a trinomial and you factor it into 2 linear factors. In that case, you're going to have some constant over one linear factor plus another constant divided by the other linear factor. If you work this out, we'll get A equals 13 and B equals -9. A nifty trick for doing linear factors is just cover up the one of the linear factors. So in this case, if we cover up x minus 3, 3 is what makes this equal 0. So if we cover this up, we're now solving for A, and if you substitute in 3, since that makes this equal 0, 3 times 4 is 12 plus 1 is 13, and then 3 minus 2 is 1, so we have 13 over 1, and we actually get A equals 13. In doing the same thing for x equals 2, if we cover up 2, then 2 times 4 is 8 plus 1 is 9, and 2 minus 3 is -1, so 9 divided by -1 is how we get B to equal -9. So when we have 2 linear factors, we can just like cover up and solve for A and B. If we have a linear factor that is repeated a certain number of times, then we have to expand by having one number over the first degree of the linear factor and another number over the repeated power, which would be in this case 2. If this had been x cubed, we'd also have a c over x cubed, and then this other linear factor, c over x plus 1, would have to be like d over x plus 1 instead. And last is if we have a quadratic factor that cannot be factored. So quadratic factors that can't be factored are going to be things like x squared plus a number, because there is no reduction for a sum of squares. So when that happens, we're going to have a linear factor over the quadratic factor. So our 4 examples are going to just cover those 3 things, and then we'll integrate. Pardon these announcements.
Mr. Watts, please dial 6245. Mr. Watts, please dial 6245.
Okay, and we're back. So for the first example, we have 4x plus 41. I'm sorry. Let's zoom in a little bit. We have 4x plus 41 divided by x squared plus 3x minus 10. So we're going to just work with the fraction part for a moment. We're going to have 4x plus 41 over, and now we're going to factor. This is going to be x plus 5 times x minus 2. And so this is going to equal a over x plus 5 plus b over x minus 2. So if we cover up the x equals -5 factor and we substitute in -5 for x, 4 times -5 is -20 plus 41 is 21, and -5 minus 2 is -7. So 21 divided by -7 is going to mean that we get A equals 21 over -7, which equals -3. If we solve for the factor that's x equals 2, then we're going to have B equals 4 times 2 is 8 plus 41 is 49, and 2 plus 5 is 7. So 49 over 7 equals 7. So our 2 solutions are A equals -3 and B equals 7. So we can rewrite this integral to be the integral of 7, well, I guess I went in the wrong order. So -3 over x plus 5 plus 7 over x minus 2 dx. And so when we integrate this, since this is some constant divided by a linear factor, it's going to be the natural logarithm. We're going to get negative 3 ln absolute value x plus 5 plus 7 natural logarithm absolute value x minus 2 plus c. If we did a u substitution, we would have, just so we're clear, u would equal x plus 5, and so du equals dx. And so we could rewrite the integral to be negative 3 dx, du over u, which would give us this integral. And we could do a similar step for a u substitution for x minus 2. It's unnecessary because the derivative is just 1, and we know since this is du over u, we're going to get a logarithm. So moving to example 2, we're going to actually have to do some algebra because we have this repeated factor. So we're going to have 5x squared plus 20x plus 6 divided by x times x plus 1 squared. So x plus 1 squared is a repeated factor. So we're going to put a over x plus, then we're going to have b over the first degree of x plus 1, and then we're going to have a c over the quadratic x plus 1. And so the proper method for solving for this is to multiply x times x plus 1 squared times all of the right side. In doing so, we will get 5x squared plus 20x plus 6 equals, so if you multiply this denominator times this, the x cancels out. So we have a times x plus 1 squared plus, if you multiply this times b over x plus 1, one of the x plus 1's cancels. So we have bx times x plus 1 plus, then if we take x times x plus 1 squared and multiply by this c term, then the x plus 1 squared is canceled out. So we have plus just c times x. And so now we're at a point where we can cleverly eliminate some constants by choosing good values of x. If we choose x to be -1, this would be 0 and this would be 0, and it allows us to then solve for c. So we're going to have one condition where we have if x equals -1, we'll even put, this allows us to solve for c. So if x equals -1, then this is going to be 5 minus 20 plus 6, which is -9. So we're going to have -9 equals, this term would be 0, and that term would be 0 if x is -1. So we're going to have just -1 times c. So negative c equals -9, which is going to imply that 9 equals c. So we'll keep track of that. So we'll put a 9 for c. Then in a similar step, so now imagine if x was 0, it would get rid of the b term and the c term and allow us to solve for a. So then to solve for a, we're going to have if x equals 0, then 0 plus 0 plus 6, we're going to have 6 equals, so 0 plus 1 is 1, squared is 1, so we'll just have a equals 6. And again, this term would be 0 and this term would be 0, so now we know a is 6. So the last step involves us replacing both a and c and choosing some arbitrary value to then solve for b. So we're going to rewrite this equation with the values of a and c substituted in. So we're going to have, pardon these announcements.
Attention to the building, there is a fundraiser going on. Krispy Kreme donuts will be sold for $1 in Commons A now until 3:45. This is for chorus. Stop by now while supplies last. Again, Attention in the building, Krispy Kreme donuts will be sold for $1 in Commons A now until 3:45 p.m. This is for the chorus. Stop by now while supplies last. Thank you.
My God. So again, sorry for the interruption. So now we're gonna replace A and C and choose some value of X that isn't -1 or 0, and then just solve for B. So we'll have 5x squared plus 20x plus 6 equals 6 times x plus 1 squared plus bx times x plus 1 plus 9x. So as long as we don't choose -1 or 0, we can solve for B because we won't eliminate any terms. So let's choose a value like x equals 1. If x is 1, then we'll have 5 plus 20 plus 6, which is 31. So 31 would equal, if x is 1, 1 plus 1 is 2, 2 squared is 4, times 6 is 24, plus, if x is 1, we're going to have 2 times 1 times b, which would be 2b plus 9. So total, we're going to have 31 equals, this is going to be 33 plus 2b, and then we subtract 33 from both sides, we get -2 equals 2b, and so -1 equals b. So so now we finally know that b is -1. So the rewrite on our integral is the integral of, so a over x. So a was 6. So we're going to have, we'll put this in focus. We're going to have 6 over x. B was -1, so -1 over x plus 1. And then C was, 9? So plus 9 over x plus 1 squared, but we're going to make that plus 9 times x plus 1 to the -2 dx. So the first two terms integrate immediately. We will get the antiderivative of 6 over x is just 6 natural logarithm x minus, this is going to be the natural logarithm of x plus 1. And imagine for a moment we did a u substitution for this. We would have u equals x plus 1, du equals dx. And so we would have 9u to the -2 du that we have to integrate. But that would just equal, if we integrated, 9u to the -1 over -1. So instead, we're just going to continue and then put plus, or minus actually, 9u to the -1, which u is x plus 1, so we'll take that out and even put x plus 1 to the -1 plus c. So our final answer is 6 natural logarithm x minus the natural logarithm of x plus 1 minus 9 over x plus 1 plus c. So for example 3, we have a quadratic divided by a linear factor and an irreducible quadratic factor. So we know that this is going to be a over x plus 1 plus bx plus c over x squared plus 4. What we will get in multiplying this to the other side is the following result. We'll get the numerator, which is 7x squared plus 5x plus 23, and that's going to equal, again, the x plus 1 is going to cancel, so we'll have just a times x squared plus 4 plus, so for the bx term, we're going to have just bx, and so we're going to have bx times x plus 1, and the x squared plus 4 cancels out for it. But then we're also going to have plus c, and c is going to be just multiplied by x plus 1 because the x squared plus 4 also cancels. So plus c times x plus 1. In a similar step, since if x equals -1, we can solve for a. So if x equals -1, then we're going to have 7 minus 5, which is 2, plus 23, which is, we're going to have 25 equals, if x is -1, -1 squared is 1, plus 4 is 5. So we're going to have 5a. And then these other two terms cancel. So that's just going to be 0. So 5a equals 25 implies that 5 is equal to a. So a equals 5. We'll keep track of that. And so then we can also say, well, what happens if, now if we use x equals 0, it cancels out the b term and leaves us with c and a. If we've already used -1, so that got rid of the b and the c. So then we're going to say if, actually, you know what? Let's go and substitute in the fact that a is 5. So we get 7x squared plus 5x plus 23 equals 5 times x squared plus 4 plus bx times x plus 1 plus c times x plus 1. If we eliminate, we can't eliminate the x. So let's say we make a system of equations where we choose x to be 1. If we choose x to be 1, we'll get 7 plus 5, which is 12, plus 23 is 35 equals, so if x is 1, this is going to be 5 times 5, which is 25. And then 1 plus 1 is 2 times 1 is 2 times b, so plus 2b and plus 2c. So we get that 10 equals 2b plus 2c. That's one equation that we need. And we can make a second equation. We said for this one, if x equals 1. So the second equation we will get is choose some value of x where we can get rid of the b term, so like 0. So if x equals 0, so if x equals 0, that's going to be 0, that's going to be 0, and we're going to have 23 equals, so 4 times 5 is 20. That term's going to cancel, and then we're just going to have plus c instead. So 20 plus c equals 23. That's going to mean that 3 equals c. So now if we know c equals 3, then we can solve for b in this expression. So over here, we're going to have 10 equals 2b plus 6. And so we subtract 6 from both sides. We get 4 equals 2b, and so 2 equals b. And that means that in this expression, we will get the integral of 5 over x plus 1 plus b was 2x. So we're going to split this, so plus 2x over x squared plus 4, and then plus 3 over x squared plus 4 dx. Oh, you can't see any of that. My bad. So we have 5 over x plus 1 plus 2x over x squared plus 4 plus 3 over x squared plus 4 as well. So let's carve out some room because we ran out of space. So if we integrate 5 over x plus 1, we're going to get 5 natural logarithm, we'll do absolute value, x plus 1, plus, this requires a u substitution where u would equal x squared plus 4. So above this, let's put u equals x squared plus 4. And so du equals 2x dx. So that's a direct replacement where we have du over u. So we're going to get another ln absolute value x squared plus 4. And then this one you should recognize as being in the form of the inverse tangent function, where a equals 2 and u equals x. So we're going to have plus 3, and then we have to multiply by 1 over a. So 1 over 2 times 3 is 1/2, plus 3/2 tangent inverse of u over a, so x over 2 plus c. So all of this is done if we have a quadratic factor on the bottom. So we ended up with the result of 5 ln absolute value x plus 1 plus ln absolute value x squared plus 4 plus 3/2 tangent inverse x over 2 plus c. So again, the integration is not difficult. It's just some of the algebra that gets here is kind of tedious, but not hard either. So for the last example, in order to do partial fractions, you must have a proper fraction, which means that the degree of the numerator has to be less than the degree of the denominator. If not, we have to do polynomial long division. And in this case, we can see that the degree of the denominator equals the degree of the top. So the first thing is we do long division. We divide this into the top. So we're going to have x squared plus x plus 1. And that divides into x squared minus x. So x squared divides into x squared once, and then we just multiply. So 1 times x squared is x squared, 1 times x is x, and 1 times 1 is plus 1. So remember, we always do the opposite. So that's going to be minus, that's going to be minus, and that's going to be minus, and we drop everything down. So we're going to have negative 2x minus 1. As a rewrite, this is going to be the integral of now 1, and then we're going to say plus, and we're going to just put the remainder over the divisor. So plus negative 2x minus 1 over x squared plus x plus 1 dx. So a thing to note is, imagine we let this equal u. So if u equals x squared plus x plus 1, du is 2x plus 1 dx. So we could easily manipulate this to get negative du equals negative 2x minus 1 dx. So now this is fortuitous in terms of how this worked out. If it didn't work out this way, we would have to do the method of partial fractions to then reduce this, but then that's going to be a lot just for this last example. So when we integrate, we're going to get the antiderivative of 1 is x, and so since this is negative du over u, we're going to have minus the ln of x squared plus x plus 1, all in absolute value, plus c. So that concludes this video on partial fraction decomposition. So we covered 3 things. We covered if we have, for example, 1, we just have 2 linear factors, which we can quickly use a cover-up method to solve for both a and b. Or if that had even been a 3rd linear factor, is c. For example, 2, we covered having a linear factor and a repeated linear factor, which required that we solve for 2 of the constants by using the cover-up method if we wanted, and then using an arbitrary value of x after substituting in the values of the 2 known constants. For the 3rd example, we had an irreducible quadratic factor and a linear factor. Now, for this irreducible quadratic factor, notice that as a denominator, it's already in the form for a tangent inverse, which is why it produced a tangent inverse as the answer. And for example 4, we had to divide to get a proper fraction, which in this case was able to be solved using U substitution, but it could have required partial fraction decomposition. My recommendation is that you complete these recs as they do produce different kinds of problems than what we did in class. Thanks.